Hello, everybody. Good morning, good afternoon, good evening, depending on where you are. Welcome to the third and final webinar of our quarter one of the financial year. That is not calendar year of the webinar world series. So today we'll be focusing on plastics and how our FTIR accessories can be used to monitor plastics at different stages of manufacture. So polymers and plastics can come in many different forms. It can come in a macro scale, such as films or recyclables, fibers and wires, or smaller forms such as pellets used as a raw material in the polymer manufacturing process, or it could be even smaller in terms of it being a smaller foreign contaminant, or the micro scale where you've got microplastics as your contaminant as well. So these polymers or plastics can be used either as a raw material in your manufacturing process, or they could be found when the bulk of the macro polymer material is broken down into them smaller segments. There are different FTIR techniques that you can use to analyze plastics or polymer samples. For example, you've got ATR. So in front of me here, I've got the SpecAC Quest single bounce ATR. That is capable of monitoring the first few microns of your sample. It's a very fast and convenient technique. And the temperature of the Quest, now that we've launched the heated puck accessory, the temperature can go up to 110 degrees Celsius. But we also have the Golden Gate accessory, a single bounce diamond ATR. I can go up to 300 degrees as well. So having these two products enables us to monitor different polymer types depending on their melting temperatures. The next technique that you could use is an external reflectance technique. So in this particular case, we're using drifts as an example, where the light scattered off the sample after penetrating into the sample, and the IR beam bouncing back into the detector is picking up the diffused components of your sample rather than specular components. But we do have a monolayer specular accessory as well for picking up any specular components of IR beam. And in the case of the drifts, we have an environmental chamber as well that can go up to 800 degrees C if that is necessary for your application. One other technique that is very common when analyzing plastics and polymers is the transmission technique, where you are analyzing the bulk of the sample rather than the first few microns of the sample, such as the ATR. So naturally, the intensity of your FTIR peaks will be a lot more strong, will be a lot stronger and more intense in your spectra when using the transmission technique. And we also have the HTHP high temperature, high pressure cell that can go up to 800 degrees Celsius for transmission analysis that requires that temperature as well. So as you can see on this slide, we have a range of accessories for analyzing a range of different sample types, such as powder samples, solid samples, liquid polymer samples, or heterogeneous samples where you're looking at the gas-solid interaction. In terms of analyzing polymer samples with ATR, you require very good contact between the sample and your ATR crystal element. So in this case, if we use the Quest as an example, you've got a loading arm that is able to put 40 pounds of pressure onto your sample and pressing it against the ATR element to provide that very good contact. And we've got a similar mechanism as well for the Golden Gate, which can go up to 160 pounds. And that good contact ensures that you have quality spectra at the end of that. But sometimes customers and users, they can neglect the importance of the anvil as well. So you can see here, for example, we've got an anvil on the loading arm, and because the end is shaped differently, that can accommodate different sample types. So on your slide, for example, on the left-hand side, you've got the flathead for powders or flat solids, polymer sheets, polymer films. In the middle, you've got a concave head for holding pellets and beads, as you can see with the concave shape of the end of the anvil in the middle. On the right-hand side, we've got a special grooved head for fibers and wires. So having the versatility of the different add-ons you can have for the Quest ATR and Golden Gate really enables you to provide quality spectra when analyzing these polymer samples. So this particular application looks at the identification of polymer blends and recycled plastics, and it's combined with chemometrics analyses to enable us to identify those blends. And in this particular case, we want to reuse your polyethylene, but before reusing it, we have to ensure the quality of the feedstock or the raw material of the polyethylene, that it's not mixed with other impurities such as polypropylene in this case. And so you can use the Quest ATR to distinguish between the two different polymers, because polypropylene and polyethylene are very characteristic bands. So polypropylene, you get some characteristic bands in the 800 to 1200 and even 1350 wave number regions that you don't get with in the polyethylene, for example. So using the Quest ATR, you can very quickly pick out those characteristic bands before performing your chemometric analyses. So the two PLS, or partial least squares component factors, were used to obtain a very good fit, as you see in figure 2 there at the bottom right-hand corner. After we've collected the spectra in figure 1 and converting that data into the plot in figure 2. And yes, so just really strong correlation there to tell us the amount of impurities, if any, in our polyethylene end product before we recycle it or reuse it, so that the properties of your end polymer product, it's not compromised by having these impurities. An extended capability of ATR spectroscopy could involve its coupling with polarizers. So in this particular example, we look at how polarized ATR spectroscopy could be used to analyze polymer thin films. So in order to investigate the long-range order of the polymer chains, we can use polarized ATR spectroscopy. And the polymers can be arranged in sheets with either random or aligned orientations. And this order can also be induced by stretching the polymer. The bottom right-hand corner shows how different orientations interact with different polarizations of light. So this example shows how polarized light interacts with ordered silk fibers. The spectra on the right-hand side show several identical samples orientated at 0 degrees in grey and 90 degrees in black. Clear differences are observed in the amide bands around 1600 wave numbers, and this can be used to determine how the degree of isotropy varies with the samples. Now we will look at the analysis of polymers using transmission techniques. So, as we mentioned before, transmission sees the whole sample and not just the surface measurement like ATR, and so this leads to increased sensitivity to minor components of the sample due to larger effective path length. And typically, when analyzing a polymer film, the thickness of the polymer is less than 500 microns. depending on the infrared absorption of the sample as well. So for example, polystyrene has a quite weak absorption, so you might want to use a thicker spacer. But for something like polypropylene, because it's quite absorbing, then you might want to use a thinner spacer. So it really depends on what sample you're analysing. And the pressing of the polymer sample into thin film requires a manual hydraulic press and also heated platens in order to provide that melting temperature and pressure to bring your polymer samples into a thin film. And by using the constant thickness film maker, you can achieve a high degree of reproducibility, as you can see here. So we've got the constant thickness film maker here, and the different rings for altering the thickness of your polymer thin film. So in terms of our solid transmission accessories, you can see them on this slide here. If you want to go into more details, you can go into the application notes as shown on the right top corner. So we have the mini film maker that can go up to 250 degrees. We've got the manual hydraulic press, automated presses, heated platens that can go up to 300 degrees C. The constant thickness film maker as seen here with a range of different ring spaces, and also the high temperature film maker as well that can go up to 400 degrees C if your sample has a higher melting point. So in terms of polymer thin film sample preparation, you can use a set of film maker and put it into a set of spec heated platens or manual hydraulic press. So for the manual press, we can go up to 15 tons or 25 tons. But if you do need varying or higher tonnages as well, we do the auto touch press that can go up to 40 tons, but they're also lower tonnages such as 8 tons, 15 tons and 25 tons as well. So just depending on what pressure you need for your sample. But in terms of the key features, this is particularly good for reproducing repeatable film thicknesses. You can quickly and easily change the film thickness with a choice of 15, 25, 50, 100, 250 and 500 micron spacer rings, as you can see here. So it's got different types of spacer rings, and it's very easy to use. You very literally just remove the top, have a bit of foil in there, put your sample in there, put your ring in, and then put the top back on. Then a film maker into your heated platens and press and apply a load to turn your polymer sample into a thin film before performing FTIR transmission analyses. And the turnaround time is really quick, so usually just 5 minutes. But if you want to speed that up even more, you can buy 2 sets of these film makers to enable high throughput work, as many of our customers do. And it's suitable for qualitative and quantitative analyses, as you will see in the next slide, and is suitable for polymers with melting points up to 300 degrees Celsius. But as mentioned before, if you do need a higher temperature, we do the high temperature film maker as well. It can go up to 400 degrees Celsius. Here we look at the film maker's capability of meeting high reproducibility. So here we just have one thickness, 25 micron thickness polypropylene with the spectra taken 5 times at 5 different recordings, and you can see very high reproducibility in this set of spectra. The filmmaker is very good at obeying Lambert's law and using Lambert's law to verify the film thicknesses. So in this particular example, as you see in figure 2, we used the filmmaker to press polyethylene at different thicknesses ranging from 15 microns to 500 microns, and then we collected the FTIR spectra, and from the 2 peaks with the asterisk on, so 887 wave number and 1303 wave number. We used those peaks to create the calibration plots on the right hand side in figure 3, where we did a plot of absorbance against film thicknesses ranging from 15 to 500 microns, and as the film thickness increased, the absorbance also increased, obeying Lambert's law. And in the calibration plots, you really do see an excellent correlation being obtained with the R² values very close to 1. So some advantages of SpecAc's constant thickness filmmaker over a traditional method such as solution casting is the fact that it provides a quicker process. It's got a more superior sample thickness control. There's a lower risk of sample contamination. There's no need to dissolve the polymer in hazardous organic solvents, improving the health and safety in the workplace or in your lab. And it saves time through less sample preparation. And as mentioned before, if you really want to optimize the throughput of your workflow to make it a more concurrent workflow, you can have multiple sets of filmmakers where one filmmaker can be in the press whilst the other one is cooling in the cooling block. So moving on from the filmmaker for transmission analyses, this is a sort of more advanced transmission accessory called the HTHP, high temperature, high pressure cell, that can go up to 800 degrees Celsius, 1000 psi. In fact, actually it works in 3 modes. So it's got a transmission mode, reflectance mode, and also decomposition mode, where you're just analyzing the vapors coming off your sample. And it's really good and ideal for sort of in situ studies where you want to be replicating real world conditions. So in this particular application, we looked at the analysis of a viscous liquid, like a resin, and you can analyze that. You can do that by smearing your resin sample onto a solid pellet before placing it into your HTHP and analyzing and observing the changes in the peaks over time as the temperature changes as well, as you can see in the top right hand corner. We also have another advanced transmission accessory called the variable temperature cell as well. That's really good for analyzing samples from sub-zero temperatures to up to 250 degrees Celsius as well. So we now move on to the analysis of polymers using IR microscopy. What can you analyze with a microscope? A lot of different things. So samples including small fibers and chips, often for forensic identification, microplastics, which is obviously a very important application now in the world we live in, due to the fact that we don't want to be harming the natural habitats, our environments, and even ourselves. We don't want such samples to be endangering human health. And it's very useful for analyzing contaminants within your end plastic product after the manufacturing process. So it's a good way to ensure that there are no such contaminants during QC of the samples. And usually the caveat of IR microscopy is that the technique suffers from low light throughput due to the small aperture of the microscope. But we at SpecAc have a way around this, as you will see in the next slide.
Hi, I'm Dr. Andrew Davis, the Application Scientist here at SpecAc. Welcome to the Newton Demo Lab. Today we're going to be talking about the DC3, the diamond compression cell. So what is the DC3 and what problems does this solve in IR microscopy? Well, to demonstrate the benefits, we will first show an uncompressed sample. As you can see, poor signal is observed through the uncompressed sample. To use the DC3, the sample is placed over the crystal. The top is then mounted and the thumb screws are used to crush the sample.
For samples that remain compressed after the load is removed, best practice is to dismantle the cell.
Then analyse the two windows to see which one has the sample on. This is the slide that we will take to the microscope. When compressed, the sample spreads out, completely filling the microscope aperture. A good spectrum is then observed. So what is a current novel IR microscopy challenge? Well, microplastics are a growing environmental concern, and their identification is an essential first step in their eradication. In order to simulate the sea and make microplastics, we stirred a vial of water with different plastics and grit for a week at 60 degrees. The artificial sea was then filtered through filter paper. In true Blue Peter fashion, here's one we made earlier. Different samples were mounted on a DC3 and measured under the FTIR microscope. A simple library match was then used to determine their identity. Thanks for watching. Don't forget to like and subscribe.
Okay, so I hope you liked that video featuring our one and only Dr. Andrew Davis, our application scientist, looking at how we can correctly use the DC3 diamond compression cell and also a very nice application towards the end of microplastics. So carrying on with the topic of microplastics, in this particular application we use the microscope and DC3 to analyze New York waters, so river water, and farmed oysters to identify the contaminants within it. So in figure 1 we identified the contaminant to be an oxidized polyethylene appearing as a white particle microplastic, and in figure 2 it's the polypropylene microplastic contaminant appearing as a red fiber in the farmed oysters and also the river water. So this application is particularly important now, especially because first of all it's telling us, the way we are manufacturing our polymer products, the quality of our polymer products, the way we're disposing our polymer products, but more recently now we've discovered that microplastics are entering the food chain and endangering human health. So for the first time in history, these microplastics are being found in the blood of humans, which was never reported before, and it just highlights the seriousness of this particular issue. And this is why SpecAC and our customers really need to collaborate and promote this sort of identification to stop harming the environment and also the health of consumers, so ourselves essentially. So yeah, I hope we can put a stop to this. So if you managed to catch our webinar last month on solutions for food and beverages, you would have seen already how the Surveyor microscope and diamond compression cell can be used for analyzing pharmaceutical tablets and also citric acid food additives, amongst other applications. So for this particular month, we want to talk about a defect found in plastic manufacturing QA. In figure 1, you see an automobile bubble part that was injection molded. So you can see that with the naked eye actually without zooming in with the microscope. But then when you go to figure 2, you can see a magnified image of that contaminant removed from the injection molding. And when FTIR is coupled with microscope, you can then see it more clearly, and the contaminant was identified as sort of a granular material. And FTIR on the right hand side in figure 3A and 3B was able to then analyze that particular contaminant to be an oily sort of silica gel material. Silica gel typically is used as an anti-caking agent, and somehow it entered the manufacturing process, contaminating the end product. So yeah, it's a very nice application here, just demonstrating how both the microscope and DC3 cells can be used together for this sort of application in quality check and quality assurance. So yeah, so that's pretty much it. Thank you guys for listening. Just before we finish, here's just a reminder that at SpecAC, we're hugely committed to a range of marketing materials with a wonderful marketing team here at SpecAC. And in the past, we have written a lot of application notes with the help of our customers, of course, such as yourselves, to talk about different applications out there in the world, the quirky applications we've seen, and how SpecAC's products can be used to accommodate those quirky applications. So please feel free to check out our range of resources. Just contact your sales representative or myself directly. And of course, if there's an application that you've seen in the field and you'd like to report back to us, so we can then further investigate and write an article on it, please feel free to collaborate with us. We're very committed to writing more and more marketing materials and providing the right tools for you to speak to your customers with in order to stimulate growth in your respective regions. And we've recently redone and relaunched our website as well. So any links that you've saved previously from SpecAC, they will no longer be valid, but you can use these links here from now on to sort of check up on any products or FTIR theory material. And also, I believe it's a lot easier now to locate different marketing literatures and application notes as well using our new website. So please do spend the time to check out our new website. It's a wonderful website. We've spent a lot of time on it, and it's been well worth it. It's very nicely done by our marketing team again. And yeah, it's very sad to say that for this quarter, we have now come to an end in terms of the Webinar World Series, but not to worry. Later on in the year, we will be doing more webinars. We've had a lot of positive feedback from all of you. Thank you so much for participating and joining our webinars and asking questions as well. So if you didn't manage to see the webinars in April and May, please contact us and we can resend those links. And for the month of June, as always, we'll be sending the link via our newsletter. And again, if you do happen to miss out on that link, then you can just contact one of us. We'll send you a privatized YouTube video to review this month's material. And here is my email address if you would like to know more about the topics we talked about today, or indeed back in April and May as well. I'm always available for a one-to-one conversation if needed. And yeah, so this is it really. So thank you again. And if you have any questions, please feel free to type them into the chat box. And I hope to see you again soon.